Hello everybody, this is Dr. Christopher White and welcome back for part 3 of Paleozoic life history focusing on the invertebrates. So before we go any further, let's just get the code word out of the way. The code word for this presentation is coffee. I repeat, coffee. That's C-O-F-F-E-E. One more time, that is coffee. So please make sure you write that down, put it somewhere safe because you're going to need it for the code word quiz. Okay, so in the previous presentation we've been looking at marine communities in the Cambrian and the Ordovician, so now we're moving on to the Silurian and the Devonian. So if you remember, at the end of the Ordovician we have ourselves a mass extinction, and the mass extinction is going to hit marine life very, very hard, and so we're going to see lots of species disappearing from the rock record. Now, these kinds of mass extinctions are absolutely great when it comes to defining boundaries in the geologic timescale, because on one side we can see lots and lots of organisms, and on the other side we can see that a lot of those organisms have suddenly disappeared all at one time. So we know that the Ordovician mass extinction was quite a big one, and it affected nearly all of the marine organisms. So after the mass extinction we see brachiopods, bryozoans, gastropods, bivalves, corals, crinoids and graptolites all rediversify. So the members of those particular groups that manage to make it through the mass extinction, they find themselves in the Silurian. Essentially the amount of competition has been significantly decreased, and so they begin to essentially evolve and diversify very, very quickly to try and fill new environmental niches. So during the Silurian and Devonian we have marine transgressions going on, creating warm shallow seas. As we've discussed, life loves those kinds of conditions, and they are also the kinds of conditions we want for reef building. So we're going to see a lot of reefs being constructed during the Silurian and Devonian. Now, if you remember, the reefs of the Cambrian and the Ordovician were normally what we refer to as patch reefs. So they were smaller reefs. In the case of the Cambrian, they were typically dominated by archaeophysids, and in the case of the Ordovician reefs, they were typically dominated by stromatophoids. Now, as we move into the Silurian and Devonian, we begin to see a bit of a diversification in the reef building fauna. So stromatophoids are still around and they're still an important part of Silurian and Devonian reefs. However, we also see tabulate corals and rugose corals becoming more important, especially rugose corals. So rugose corals come in two forms. We have individual rugose corals where you can see, this is obviously the top of the organism. There's the void in the middle where the organism itself would live. You can see it there in section. And the organism itself has this very, very distinctive horn-shaped exoskeleton, shell. Now, rugose corals can come in two forms, individual or colonial. And so you can see in this instance what we have are multiple rugose corals all stacked next to each other, forming essentially this mound-like structure. So if we look at this artist's impression of a generalized community for the Silurian and Devonian, we're going to have reefs which are going to be made of stromatophoids and tabulate corals and rugose corals. We're still going to have the trilobites around. They're still doing well. We have the Eurypterids. If you remember, the Eurypterids just started to put in their appearance right at the end of the Ordovician, but in the Silurian and the Devonian they begin to become quite common. In terms of the Eurypterids themselves, they're a very interesting group because they evolved not only to live in salt water and fresh water, but we also have numerous examples where we can see Eurypterid tracks on essentially exposed sediment. So they would have actually walked onto the continents probably for short periods of time. We also have the evolution of fish, but of course they are vertebrates, so we're not really going to worry about those right now. They're going to be in the second presentation. We have crinoids still doing their thing. And if we look at the general makeup of the Silurian and Devonian communities, things are beginning to become a little bit more normal looking. Granted, Eurypterids are a very alien-looking organism, but when you look at them, you can see quite clearly they're part of the arthropod phylum. You can see the fish look like fish, the crinoids look like crinoids. So everything's starting to become that little bit more familiar to us. So in terms of the Eurypterids themselves, they're part of the phylum Arthropoda, and they make their first appearance in a big way during the Silurian. Now, they have a very, very distinctive, what's referred to as a scorpion-like body. So you can see it here. Here we have a couple of Eurypterid fossils. You can see this is going to be the head at this end. You can actually, this particular example here is actually on its back. So you can see the legs right here. Okay, so it has these two rather large paddles here, they would have been moved primarily, they were used primarily for propulsion, so they would have been used to essentially row the organism across the seabed. And then you have this long segmented body, which tends to end in what looks like a scorpion-like stinger. Now, it's not actually a stinger. Chances are it was probably used more for defense than for attack. But nevertheless, you know, a lot of these Eurypterids do tend to end in a pointy appendage on the end of their tail. So Eurypterids are particularly important to us because they're one of the first species where we can see them really going from saltwater environments into freshwater environments. And as I've said, in some instances, we even have Eurypterid tracks on exposed sediments. They're actually leaving the water and they're moving around on the continent. Now, chances are they weren't on the continent for extended periods of time, but, you know, that it nevertheless shows that life is starting to go, right, well, you know, the oceans are getting quite full now. There's all that continental crust over there where not much is going on. Maybe it's time to try a new environment out. Now, also in the Silurian and Devonian, we have the rise of the ammonites. So they're part of the cephalopod group. That's the group that includes nautiloids and cuttlefish and octopuses. So the ammonites begin to develop from nautiloids in the early Devonian, and they very rapidly diversify. And when we look at the Mesozoic, you will see that ammonites become a massively successful group. Now, ammonites are once again excellent fossils when we're doing biostratigraphic correlation. They were very, very widespread. There were numerous species, and those species tended to be relatively short-lived. And so they're absolutely great for tying up rocks of the same age over large distances using fossils. Now, in terms of the ammonites themselves, as I say, they make their appearance in the Devonian. In the Devonian and the Permian, they become more and more important. By the time you make it into the Mesozoic, they are extraordinarily important parts of the marine community. So, you know, by the end of the Mesozoic, so by the end of the Cretaceous, they are one of the most dominant organisms in the marine environment. Now, in terms of the ammonites themselves, you can actually, you know, crudely date them based on things called suture lines. So suture lines are essentially patterns that form on the shell. Very early ammonites tend to have very, very simplistic suture lines, so just, you know, gently undulating lines, whereas ammonites which are later, so, you know, Jurassic and Cretaceous, tend to have extremely complex, extremely convoluted suture lines. So it's a very simple way of, you know, approximately dating how old your ammonites are. And the Eurypterids and the ammonites in particular become, you know, very, very important, very, very noticeable species in the Silurian and Devonian marine communities. So the end of the Devonian was marked by another mass extinction, and the extinction did substantial damage to reef communities. However, land plants appear to have been relatively unaffected. Now, this is an important point. So what this would suggest is that whatever's going on to cause this extinction is primarily focused on the oceans rather than the Earth as a whole. If it was focused across the entire Earth, it would affect both marine and continental groups of plants and animals. However, in this case, it appears to be mostly focused on marine communities. We also see that marine communities in tropical regions were more affected than those in more temperate climates. So this would suggest that what we're looking at is a mass extinction caused by decreasing ocean temperatures. And so these decreasing ocean temperatures are naturally going to make it more difficult for tropical organisms to survive. Because remember, as ocean temperatures decrease, the band of warm water around the equator will get narrower because colder water will start to push southwards from the North Pole and northwards from the South Pole. And so it will begin to constrict this equatorial band of warm water. And of course, if there's less equatorial warm water, that means there's less space for these tropical organisms to live. They have to compete with each other more, and so that means you're going to see more and more of them becoming extinct as they become outcompeted. So this would suggest that the Devonian mass extinction is probably primarily due to a change in global ocean temperatures. The communities were also affected by the closure of the Iapetus Ocean, and other orogenic events. So we have several mountain building events which are going to take place during this period of time. And obviously when the continents come together and they suture together to form land masses, what's going to happen is you're going to lose passive continental margins. They're going to be destroyed. And this once again is bad for marine life, because marine life loves these nice, safe, boring, passive continental margins. And as soon as you start to remove them, that's going to be a problem. And once again, that means there's less room for marine life. That means, there's more life in a smaller space. They have to try and compete with each other, and that will lead to extinctions as species begin to be outcompeted. So once the Devonian is done, obviously we're going to move on to the Carboniferous and the Permian marine communities. So as with the previous mass extinctions that we've had, marine life is going to rapidly recover in the early Carboniferous, and it's going to re-diversify. So the species that have made it through the mass extinction are going to suddenly have a whole range of environmental niches open to them, and they're going to very quickly adapt and diversify to try and fill those niches. In terms of the marine communities during the Carboniferous and the Permian, we're going to see the ammonites becoming more important. So if you remember, ammonites are nectonic organisms. So they're actually moving around in the water column. And so in terms of organisms that are actually moving through the water, we've got the ammonites and we've got the very early fish, and we also have some of the cartilaginous fish, what we know as sharks, will also be moving around during this period in the water column. On the seafloor environment is going to be dominated by a range of organisms. Brachiopods are still very, very important. We also have the crinoids, so they're a type of filter-feeding organism that's attached to the seafloor, and the bryozoans, also a type of filter-feeding organism. And we're going to steadily see the crinoids and the bryozoans increase and diversify throughout the Carboniferous and into the Permian, and they're going to reach their peak in the Permian. Now, in terms of reef-building organisms, the stromatophoids, the tabulate corals and the rugose corals of the Silurian and Devonian are never really going to recover from the mass extinction that occurs at the end of the Devonian, so they're hit pretty hard. So this means we begin to see a change in the reef morphology. So in the Silurian and Devonian we had quite long linear reefs. However, as we move into the Carboniferous and the Permian, we begin to see the reefs becoming a bit more patchy, they become a bit more isolated, and they're more like giant mounds than long linear structures. Now, in terms of the reefs themselves, they are dominated by crinoids. So once again, here's a picture of a crinoid in the background of this image, background of this slide, sorry. We can also see there are large amounts of blastoids. A blastoid is a type of echinoderm. If you remember, echinoderms are the group that includes sea urchins and starfish. We also have the bryozoans, they're coral-like organisms. We have the brachiopods, we've spoken about them before, and we have a range of calcareous algae, so stromatophoid-like organisms. And so all of these organisms combined are going to go to form reefs. So what you have is you have a far more varied reef building community compared to the Cambrian, the Ordovician, the Silurian and the Devonian. So within this time period, the carbonate remains from bryozoans and crinoids produce massive amounts of skeletal remains. So there's, these reef communities produce huge quantities of skeletal material. And this skeletal material essentially builds up to produce massive layers of fossiliferous limestone, which are especially common during the early Carboniferous. Now, in terms of Permian communities, they are essentially a continuation of the Carboniferous communities, but on the whole, they're smaller. Now, the reason for this is we have the continents are coming together to form the supercontinent of Pangaea. This once again decreases the amount of passive continental margins available for life, and so that's going to mean, less passive continental margins means less room for life, means greater competition, and therefore more extinctions. So during the Permian, we see the appearance of the productids. These are a group of spiny brachiopods, and they become the dominant brachiopod species. So they become extremely important. Now, the fact they're spiny tells us something about what's going on. Spines obviously mean you're on the seafloor because a spine is there to protect yourself. So if you cover yourself in spines, that means you're trying to fend off predators. And so this would suggest that rates of predation for brachiopods during the Permian are quite high. And so these organisms very quickly develop, a spiny shell, which will help to defend them from, attacking predators. We also see the appearance of the fuselids, and they're a type of spindle-shaped foraminifera, and they become more common and more diverse from the late Carboniferous into the Permian. And you can actually see some of them here for comparison. So there they are, and this is a quarter for a size comparison. They're pretty small things, and they would have lived in the water column. And you can actually see a microscopic photograph of one right here. And the organisms themselves, foraminifera, are zooplankton, so they're technically predators. And so they would have floated around in the water column, eating other smaller animals. Now, in terms of the fuselids, they actually make very helpful fossils when it comes to biostratigraphy, because once again they're very widespread. There were numerous species, and most of those species are quite short-lived, so they're absolutely perfect for correlating layers of rock over large distances. So we've spoken about the mass extinctions, and now we actually need to take a few seconds and really think about them. So when we look at mass extinctions, we notice the following things. They typically affect both land and marine life. So this suggests that whatever's going on is a global problem. Obviously, if it was more localized, it would only affect a limited environment, like either the oceans or the land. We typically see in most cases tropical organisms are often more affected than organisms from higher, more temperate latitudes. Once again, this makes a bit of sense. Most of the time when it comes to a mass extinction, the environments that tend to get affected most are the equatorial regions, typically because there'll be some kind of change in water temperature associated with the mass extinction event. And this will often mean that more temperate organisms will start to move towards the equator. They will displace the tropical organisms, and so the tropical organisms get squeezed into a smaller and smaller area, and that's obviously going to lead to more competition and more extinctions. We also see that although some groups within a phyla will become extinct, the phyla itself will persist. If the phyla didn't persist, they wouldn't have made it to the present day, but they do. So what we can see by this point is, yes, mass extinctions do affect all phyla. However, you can be certain that at least one species from each phyla will make it through, and so they will be able to continue that group of animals forward. So when we look at the fossil record, we see the Paleozoic had several mass extinction events which dominantly affected marine invertebrates, so trilobites, brachiopods, bivalves, and that's not really a huge shock because the continental flora and fauna would have been relatively limited for most of the Paleozoic, and so most of the life is actually going to be in the marine environments. And so obviously when a mass extinction occurs, we're going to see those mass extinctions most strongly in the marine environments. So in terms of the big Paleozoic mass extinctions, we obviously have the Ordovician Silurian mass extinction that affects all invertebrates. We have the Devonian Carboniferous mass extinction. That's particularly hard on reef-building organisms, so that's going to be your stromatophoids, rugose corals and tabulate corals. But it also has a pretty serious effect on the a group of organisms called the armoured fish, also take a bit of a beating at the Devonian Carboniferous mass extinction. And then we have the big one, right at the end of the Paleozoic, the Permian Triassic mass extinction. In this case, up to 96% of all marine invertebrates and greater than 65% of all land animals become extinct. This one is the big one. It's the largest extinction that has ever occurred in Earth history. Now, the best known mass extinction that most of us will be familiar with is, of course, the KT mass extinction, which occurs at the Cretaceous-Tertiary boundary. This is the one that kills off the dinosaurs and the flying reptiles and the marine reptiles. Now, although some extinctions like the KT mass extinction were rapid, so if you remember, the KT mass extinction is caused by meteorites hitting the Earth, and that, by geologic standards, is a very fast process. However, in most cases, mass extinctions will actually be quite slow when we think about them on a human timescale. Geologically, they're quite fast, but from a human timescale, they'll tend to take, a few million years. In a lot of cases also, one single cause is often not to blame. In most cases, the mass extinction is due to some kind of environmental change, and environmental changes are often the result of numerous factors changing. And so this will lead to one large overall change in the environment, and that will drive the mass extinction. So environmental changes will obviously have numerous effects on both marine and terrestrial habitats, and so that's why we tend to see both of those environments affected during mass extinction events. Okay, so the Permian-Triassic mass extinction, also referred to as the Permo-Trias mass extinction. So the numbers, so these are maximum estimates for what was affected. 96% of marine invertebrate species become extinct. 50% of marine invertebrate families become extinct. 70% of terrestrial vertebrates become extinct. Those are organisms on land that have spines. Greater than 65% of all land animals become extinct, and 33% of insects become extinct. So this was a really big mass extinction event. So the rugose corals and tabulate corals, they held on from the Silurian and Devonian into the Carboniferous and the Permian. They're gone. The fuselids, they're gone. Numerous bryozoan species and brachiopod species, they're gone as well. It's a really, really big mass extinction event. Now, the cause of this mass extinction and its duration actually remain relatively uncertain. So geologists tend to fall into two groups when it comes to the Permo-Trias mass extinction. The first one is the catastrophic group, and they say whatever caused the extinction occurred relatively rapidly. And then you have the gradual group, who argue that there was a build up to the extinction, and these build-ups, these events slowly built up over time, and then eventually you hit a tipping point, at which time the mass extinction event occurred. So geologists must explain why the extinction had a very long recovery time. So it takes between about 4 to 6 million years before we begin to see plants and animals actually recovering from the Permo-Trias mass extinction, and it actually takes about 30 million years for a full recovery of the terrestrial vertebrates. So, these communities were hit very, very hard, and it took a very long time for them to get back to the kinds of levels that we saw before the Permo-Trias mass extinction. So why the extinction event, we also need to explain why the extinction event affected marine organisms with calcium carbonate shells at a higher rate than organisms with non-calcium carbonate shells. So what are the things that we know occur at the Permo-Trias mass extinction? Well, we know that there's a marked decrease in the carbon-13, carbon-12 ratio. What this is telling us is it means there's less life. So carbon-12 tends to accumulate within organic material. So obviously, if there are fewer plants and animals around, that means less carbon-12 being locked up in organic molecules. And so this is going to obviously affect the carbon-13, carbon-12 ratio. We also see approximately an 8 Celsius increase in global temperature. That is a very big increase in global temperature, and that's going to have a very serious effect on both the continental and the marine environments. So you're probably going to see the continents becoming drier because of this increase in temperature, and you're also going to see the oceans becoming warmer. We also see an increase in global carbon dioxide levels from about 20 parts per million to about 20 parts per million. To give you some idea, the concentration of carbon dioxide in the Earth's atmosphere before the Industrial Revolution was about 200 parts per million. So you can see, once again, we have this huge quantity of carbon dioxide in the atmosphere. That's obviously going to lead to a substantial greenhouse effect. We seem to have indications of ultraviolet radiation levels increasing. This could possibly suggest there's something going on with the Earth's ozone layer. We also see a spike in marine and terrestrial fungi, and this one's quite an obvious one. When you have lots and lots of dead plants and animals, that means you're going to have lots and lots of organisms to decompose them, and of course one of the main groups of decomposing organisms are the fungi. So the fact that we suddenly see the fungi begin to increase in number during the Permo-Trias mass extinction isn't really a huge shock. And we also see the continents becoming more arid, and this will actually tie back to this increase in global temperatures. So, these are the effects that we can see quite clearly, and so we have to begin to explain, what are the mechanisms that could be causing these changes. So, are there any causes for the Permo-Trias mass extinction that we can just reject straight away? Well, there's two. The first thing we can reject is a reduction in the size of the continental shelf environment. So we've already been discussing how the continents are coming together, they're forming larger land masses, and this means we're getting rid of passive continental margins. And this in theory could be the cause of the Permo-Trias mass extinction. However, that doesn't actually work. The problem is that we've seen these continental collisions occurring all through the Paleozoic, building up to Pangaea forming towards the end of the Paleozoic. And when we've seen these collisions in the past, they haven't really had this level of an effect on the marine community. So it just doesn't quite work as a possible cause for this mass extinction. We can also reject glaciations and their effect on sea levels and ocean temperature as a possible cause. And the reason for that is because the glaciations that occurred during the Carboniferous had been waning in the Permian, so on the whole, global temperatures had actually been going up. And so this means that ocean temperatures would have been a little bit warmer. It would have meant there would have been more water in the oceans as well. That would have meant a higher sea level, which would have led to the formation of these these empiric seas, these shallow warm bodies of water. And so as you move from the Carboniferous to the Permian, conditions are actually getting a little bit more advantageous for life. So you should actually see life becoming more common, not becoming less common. So what are the options that are left to us? Well, the first option is arguably the one that our minds will go to first, a meteorite impact of some kind. Now, this would explain the rapid extinction, just like the dinosaurs. Our problem is this though. As this mass extinction would have occurred some 250 million years ago, the evidence for this impact would likely have either been destroyed or concealed. So we need to remember that oceanic crust is recycled approximately every 200 million years. This means that oceanic crust from 250 million years ago has been destroyed. So if the meteorite impact in question was to occur in the oceans, we wouldn't see it because the oceanic crust on which the crater is located has been destroyed. So that's a bit of a problem. The other thing is that if the impact occurred on land, well, chances are the crater has been eroded down, it's been filled in with sediment, and therefore that makes it more difficult to see. Now, at the moment we have no impact crater which would be sufficiently large enough or of the right age to have caused a global mass extinction. Okay, so we don't have a really big impact crater like the Chicxulub impact crater which produced the KT mass extinction. That's our first problem. Now, we do actually have an impact crater that's about the right age, and it's this crater here, and I'm not going to try and pronounce it because I'll get it horribly wrong. Now, the problem is, though, is this particular crater is too small. It's not big enough to cause a global mass extinction. However, the area in which the impact occurred is an area which is quite rich in oil shales. So these are shales which are very organic rich and they contain hydrocarbons. So a large impact into that kind of strata, this kind of very hydrocarbon rich material, could possibly lead to the release of substantial quantities of carbon dioxide and methane, and this would obviously lead to global warming. And of course, one of the things that we see is an increase in global carbon dioxide, an increase in global temperature, and that obviously causes the continents to become more arid. So an impact into these hydrocarbon-rich rocks could possibly have triggered the mass extinction. However, at the moment, it doesn't seem like the most likely explanation. It's a possibility, but it doesn't really work with the evidence that we have. So what's our next option? Well, the next option is a stratified global ocean. So in a stratified global ocean, what happens is we begin to see the layers of water in the oceans becoming separated from one another. And the classic example of that kind of situation is if you've ever been to an open air swimming pool, you might have felt the water on the top of the swimming pool and it might have felt relatively warm. Of course, what happens then is you then jump into the swimming pool and you punch through this layer of warm water at the top, and then you enter the layer of cold water directly below it, and all of a sudden you find yourself in freezing cold water. So this is an example of stratification. You have this layer of warm water at the top, and that layer of warm water is operating independently of the layer of cold water below. And so if you can stratify the ocean, that's obviously going to have an effect not only on water temperature, but also the amount of oxygen. because the oceans require waters to constantly circulate, to constantly bring food and oxygen into deeper parts of the ocean. However, the thing is if the ocean begins to stratify and layers of water begin to operate independently of each other, it means they're not going to be mixing with each other. This means that the water at the top of your water column is going to be normal oxygenated seawater. However, the water below that level is not going to have fresh oxygen being brought in to replace the oxygen that's lost. And so this could possibly lead to oxygen concentrations in deeper waters becoming a lot lower, possibly all the way to anoxic conditions, so oxygen free. So there's another problem here though. Because the water at the top of your ocean column is getting warmed up by the sun, it's going to get hotter. Now, normally that would be mitigated by the fact you would have colder water mixing with it. However, if that mixing isn't happening, that means your surface water is getting hotter and hotter and hotter. And because it's getting hotter, it means it's becoming more buoyant, so it refuses to sink. If it doesn't want to sink, it won't mix with the colder water below. And so, this decrease in deeper water oxygen levels and the warming up of the water at the top of the water column is going to make it more difficult for water to mix, and it's going to have a very, very serious effect on life, because organisms that live in deeper water are suddenly going to find themselves struggling with low oxygen conditions, whereas organisms that live on the water surface are suddenly going to find themselves having to deal with very, very high water temperatures, and both of these are very, very big problems. So just to give you some idea of what we're talking about, here's a diagram that shows you changes in ocean temperature between the winter and the summer. So in this area you can see this is the winter, you can see the ocean temperature is on the whole relatively homogeneous. Move into the summer on the other hand, you can see this upper layer of water is obviously being heated up, and so it becomes a lot warmer when you compare it to the deeper water. Now, one of the things you'll notice though is of course you have this interface between the two. So this body of water up here is operating independently of this body of water down here. And this is normal. But this kind of stratification, the layers don't separate themselves perfectly, and this type of stratification will normally only last for weeks, maybe a few months. So in the grand scale of things, it's not, that serious. The type of stratification we're talking about would have lasted, for, thousands of years, millions of years. And so obviously that would have a very serious effect on these deeper marine communities and these surface communities. So this stratified ocean is a very, very big problem. Now, this can then lead to these low-level oxygen conditions. So this can cause what's called an oceanic anoxic event. So this would mean that, although you would have oxygenated water up at the top of your water column, all the water below it would steadily over time become more oxygen poor, eventually leading to anoxia, so the water becoming more or less oxygen free, and that's obviously going to lead to any oxygen dependent life dying out. Now, this obviously means that you're going to have large quantities of organic material being deposited on the seabed because of all these animals dying, and of course that's then going to lead or encourage the formation of sulfate reducing bacteria. So this is a type of decomposing organism that instead of using oxygen to respire, it uses sulfur instead. This means it can obviously survive in water that's pretty much oxygen free. Now, one of the problems is that these sulfate reducing bacteria produce hydrogen sulfide as a byproduct. Hydrogen sulfide, when you mix it with water, forms sulfuric acid. And so what's going to happen? Well, if we start producing huge quantities of hydrogen sulfide, that's going to lead to the formation of large amounts of sulfuric acid, and that's going to cause the pH of the oceans to decrease. Okay, so the water is going to become more acid. This could possibly explain why we begin to see organisms that have calcium carbonate shells becoming more affected during this mass extinction, because calcium carbonate will naturally react with sulfuric acid, and that would mean that a calcium carbonate shell wouldn't really be the best choice because it would constantly be reacting with the seawater. So this is, this is all, due to this oceanic stratification. So the stratification leads to poor mixing, which leads to an oceanic anoxic event, and then that leads to, large numbers of sulfate reducing bacteria that help to drive down the pH of seawater. At the same time, we have this period of global warming, so we can see that the Earth as a whole is getting hotter. Now, this increase in global warming is obviously going to help to contribute to the formation of a stratified ocean, especially as the temperature gets even higher, and this is obviously going to inhibit the mixing of seawater, which is then going to lead to this oceanic anoxic event. It would also help to contribute to what's called a stagnant ocean, which is when the seawater isn't mixing. Now, also, because the way by which the seawater is circulating has changed, this is also going to have an effect on global weather patterns. Because you may not know this, but the weather patterns that we see in the atmosphere are partially affected by the circulation of water in the oceans. They have an effect on what goes on in the atmosphere. So if we begin to change how the water circulates in the oceans, that is going to have a direct reflect on the environment. And so we may well see global warming leading to, changes in weather patterns that begin to produce effects such as the drying out of the ocean, the continents. We begin to see the continents becoming drier. So the question is, well, why do we see this global warming? And there's a few reasons as to what could be causing this global warming effect. So the first possibility are gas hydrates. So gas hydrates are minerals that are made up of methane and water. And gas hydrates actually form naturally on the seabed, but they are stable as long as the water is cold and as long as the pressure is high. So what would happen if you have gas hydrates in an area that suddenly finds itself becoming a lot warmer? So if we just go back to the previous slide, imagine, you have gas hydrates in an area like right here. Okay, under normal conditions, the water is deep enough and cold enough for the gas hydrates to be stable. However, as this area begins to get heated up because the atmosphere is getting warmer, all of a sudden the gas hydrates here begin to break down. And when they break down, they begin to release the methane. And methane is a very powerful greenhouse gas. It's way more powerful than carbon dioxide, about 20 times more powerful, I believe. So the release of large amounts of methane into the atmosphere due to these gas hydrates melting would help to encourage a sudden and very strong increase in the greenhouse effect. We also, during the late Paleozoic, have huge amounts of volcanism going on. And a lot of this volcanism is associated with rift volcanism in the area of what is now modern-day Siberia in Russia. And this area is called the Siberian Traps. And it's an area of approximately 2 million square kilometers. So it's a huge area. And in this area, during the late Paleozoic, we have huge rifts in the Earth's surface, and massive amounts of mafic lava, so basalts essentially, are pouring out of these rifts onto the surface of the Earth. And so these huge rift volcanic eruptions are obviously going to release huge amounts of carbon dioxide. That's obviously going to affect global warming. And it's also going to affect ocean temperature as well, because some of this carbon dioxide is going to dissolve itself into the oceans, where it's going to form carbonic acid. Once again, that's another acid, and that's going to help to drive down the ocean pH. At the same time, volcanic eruptions will also release chlorine and fluorine during the eruption. Now, chlorine and fluorine levels during eruptions tend to be relatively low on the whole. However, when you have absolutely huge eruptions, although they're relatively minor components, the amount of them that's released in total could be very, very high. Now, the thing about chlorine and fluorine is that they will enter the atmosphere, and they really love to react with ozone, and they will destroy ozone when they react with it. So an increase in chlorine and fluorine levels in the atmosphere would lead to a reduction in the amount of ozone in the atmosphere, and this is going to affect the ozone layer, and that would then produce the observed increase in ultraviolet radiation. So we also need to remember that once again, as part of these volcanic eruptions, we have this carbon dioxide that's going to mix with water in the atmosphere to form carbonic acid. We're going to have some hydrogen sulfide being released by this volcanism as well. That's going to mix with water in the atmosphere to produce sulfuric acid, and so this is going to lead to acid rain. So that's when water in the atmosphere becomes more acidic. The rain that forms from that water obviously falls to the ground, it enters the soil, and because of the acidic nature of the water, it begins to decrease the soil pH. It kills off the roots of plants, and it also kills off single-celled organisms in the soil, essentially destroying the soil community. And so that means essentially the soil becomes ineffective. It can't support life, and so where you have very, very bad acid rain, it will literally kill everything in the soil. The plants will die, the microorganisms in the soil will die, and you'll have a pretty barren, life-free environment. But don't panic, it gets worse. It just so happens that the area in which the Siberian traps are forming, so all of this volcanism is taking place, happens to also have extensive coal beds in the area as well. And so what happens is you have magma moving through these coal bed rich rocks. They're going to heat up the coal bed rich rocks, and that's going to lead to the maturation of the coal deposits, and that's going to produce the release of huge amounts of carbon dioxide and methane, which once again are going to go into the atmosphere, and they're going to increase global warming. And then the final thing that's happening is we begin to see the continents becoming drier. Now, we've already discussed how part of that is going to be due to changes in weather patterns caused by changes in ocean circulation, but it's also going to be a result of the formation of Pangaea. So typically the larger your continent is, the drier the center of your continent will be, because it's further from the sea. So that means that when you look at a normal continent, most of the time you'll see the wettest environments will be close to the coast, and the driest environments will be further inland, because the air has to travel further to get there, and so by the time it makes it there, it will have dropped most of its water in the form of rain, at some point in the past. So by the time the air gets to the center of the continent, it will tend to be pretty dry. So the formation of the supercontinent of Pangaea, combined with the formation of several mountain ranges, which will affect how air is circulating in the atmosphere. On top of that, combine it with the change in circulation in the oceans, that's going to lead to, in some instances, less rainwater falling on the continents, and so we're going to see a corresponding increase in the amount of desert environments. And obviously life doesn't really like desert environments, and so that's also going to be a bit of a problem. So what you can see here is at the end of the Permian, essentially things were going badly wrong pretty quickly. So to give you some kind of basic idea of what could be going on, now this is just a very basic rundown, so let's go with. So we have volcanism or maybe some kind of meteorite impact. This leads to the release of large quantities of carbon dioxide, chlorine, fluorine and hydrogen sulfide. Also, if we have volcanism, that in the Siberian Traps area, that's also going to lead to the coal beds being heated up. That's going to produce even more carbon dioxide and methane. This is all going to lead to global warming. This is going to lead to a stratified ocean, so that's going to reduce ocean mixing. That's going to lead to an oceanic anoxic event, and that's going to lead to increasing amounts of sulfate-reducing bacteria, producing more hydrogen sulfide. All that hydrogen sulfide is either going to enter the ocean, in which case it's going to decrease the ocean pH, or some of that hydrogen sulfide will make it into the atmosphere, where it will form acid rain, which will then poison plants and animals on the land. This is all obviously going to lead to a mass extinction. This is going to lead to a decrease in the uptake of carbon-12, because obviously we've got less life, and so this is going to produce the carbon-12, carbon-13 ratio change that we see, and this is then obviously going to lead to larger quantities of dead animals, which means more organic material to decompose, which means we see an increase in the amount of fungi. So as you can quite clearly see, it all went terribly, terribly wrong at the end of the Permian. Now, we need to remember that just because the extinction was rapid, it doesn't necessarily mean that the event or events that caused the extinction must also be rapid. So there was probably a process, or so a build-up of each of these factors over time, and you will have eventually come to a tipping point. And once you make it to that point and you go over it, that's when the mass extinction itself actually occurs. So chances are, before the mass extinction event actually happened, there probably was quite a long build-up. However, once you actually make it to the, once the correct conditions are achieved, then the mass extinction occurs very, very quickly, and as discussed, it has a very serious effect on life during the Paleozoic. Okay, everybody, so that's it for Paleozoic invertebrate life. So keep an eye out for the next presentation, where we'll be looking at Paleozoic plants and Paleozoic vertebrates.